Hey everyone, today I want to talk a little bit about exponential functions. At the end of this video, I'm hoping that you guys will be able to solve exponential functions. Look at some properties that we talked about in the past, but it has been a while since we've seen them. And also we'll look at some real-world applications, specifically with growth and decay models. So to start us off today, what is an exponential function? So an exponential function is a function where the variable is located as an exponent. And then the base of the function is a positive real number that is not equal to 1. And it's really important that our base is not equal to 1 because if it is, then we're not actually growing or decaying at all. We're just kind of staying constant because 1 to any power is just 1. So we got to make sure the base is either larger or smaller than that. And again, it's always going to be a positive. Our base is never going to be a negative value. All right, so let's look at some examples and determine if the function is exponential or not. The first one is 2x cubed, and this is not an exponential function. Right, the reason that this one is not an exponential function is because there is a 3 in our exponent and not a variable. Therefore, it's not an exponential function. The second one is 4 to the x. This one is an exponential function. So that one we would answer yes. The third one, which is 1/3 to the x power, that is an exponential function. It's okay that your base is a fraction, so you can have a fraction for your base as long as it's positive. Notice that the variable, again, is in the exponent, so that's what classifies it as exponential. The next one is not. There is no exponent that has a variable. So notice x is our variable, but it's not up as an exponent. And then the last one is no. That is also not an exponential function. Again, the exponent is a -1 and not a variable. All right, let's see if we can actually create an exponential function if we're just given a set of data here. So if I'm looking at my x value and my y values, and notice that this is in function notation, so it is a function, it seems to be increasing, right? Your x values are increasing by 1, but your y values, it's not increasing by a constant number, right? It's not like we're adding 16 each time, or we're adding 64 each time, or whatever it may be. So because we're not adding the same number each time, we know that it's not linear. So the next thing we look at is, are we multiplying by the same number each time? So to figure that out, we would do 64 divided by 16. And we get an answer of 4. So in the first round, we multiply by 4 to get the next value. Let's see if that holds true from here on out. So 256 divided by 64 gives me 4 again. And it is. Okay, so my pattern is holding true here. I'm multiplying by 4 each time. So because I'm multiplying by 4 each time, and I can go back around here too, so that'd be 1 and 4, we would say that this is exponential. And the function we can create would be 4 to the x power. So 4 is considered our base. It's what we're multiplying by each time. And x is our exponent there. So how many times have we done that? Have we done it 1 time? Have we done it twice? Have we done it 3 times? So this is how we can represent that function. In fact, let's do f of x equals that. That way the notation is proper now. All right, so how can you actually solve exponential equations? So if I move this up a tad here, we can see my steps. The first thing we want to do to solve exponential equations is make sure that they have the same base. So you're going to have something on both sides of your equal sign. And we want to make sure that those values have the same base. All right? If they don't, we need to rewrite it so that they do have the same base. We'll see an example of that in a minute here. Once they have the same base, the math works its magic and the bases drop out. Okay, and once you have that same base and they drop off, you're just left with what was in the exponents. And then you solve for the variable that you have in your exponents. All right, there are some helpful properties that we need to remember when we are dealing with solving exponential equations, and hopefully you can remember some of these from our Algebra 1 days. Well, let's take a look here. The first one is the product property, and that says when multiplying two of the same variable, you're going to add the exponents. So what that means is if I were to have 2 to the x power times 2 to the 4th power, we can go ahead and say that is 2 to the x plus 4 power. Notice how they have the same base, and when you're multiplying there, we add those exponents. Now, the quotient property is when you're dividing, then we subtract the exponents. So if I have 2 to the x divided by 2 to the 4th, that's 2 to the x minus 4. So you're actually subtracting those exponents there. But notice you're keeping the same base of 2. The power of a power property would be 2x to the 4th. And you're going to multiply your exponents there. Again, notice how there's not a second base that's in between the x and the 4 this time. That's how I know that it's a power of a power, because there's no extra base in there. So if you look back up to the product property, notice how there's a base here and a base here. We only have one base there. So that's when we know we got to multiply that. So we get a 4x there. Okay. And last are negative exponents. So if I were to have 2 to the negative x power, we are going to represent the reciprocal of that base. So we just kind of knock it down to the denominator, and it would become positive there. Okay, so those are going to be really helpful when we go to actually solve our exponential equations. All right, let's take a look at solving one. So here I have the square root of 11 to the 12x power equals 121 to the x plus 1 power. So I want to write these so they have the same base. All right, right now the square root of 11 and 121 are not the same base. In fact, I don't even like how the square root is there. So what I'm going to do is I'm going to rewrite that. Now don't forget that the square root of something is really to the 1/2 power, right? So the square root of 11 can be written as 11 to the 1/2 power. So all I did here was rewrite the square root of 11 as 11 to the 1/2 power. Notice how the 12x is still kept kind of on the outside of my parentheses. All right, 11 is my base here. I can rewrite 121 so that 11 is the base. And in fact, to do that, 11 squared is 121. Now that they have the same base, my bases drop off and I'm left with my exponents. But before I do that, let's just kind of clean up our exponents a little bit. So here is a power of a power, right? So we need to multiply our exponents. So 1/2 times 12x is my 6x. And I also have a power of a power over here. So we're going to distribute the 2. So really that would be 11 to the 2x plus 2 power. So now that I've cleaned that up, now my bases are going to kind of drop off. And I'm left with 6x equals 2x plus 2. And here, we're going to work on solving for x. So let's subtract the 2x from both sides. and divide by 4. And we get x equals 1/2. Okay. Now you can go ahead and check your answers. In fact, you should by substituting them back into your original equation and see if you get a true statement there. So it's always wise to substitute back and make sure that that works out. Okay, I still want to talk about exponential growth and decay. So exponential growth and decay are kind of our real-world applications that use our exponential functions. So exponential growth, and you may have heard about this in your science courses, but exponential growth is when your initial amount grows significantly as time passes. And we see this with maybe bank accounts, or we see it with like bacteria, or whatever it may be. Decay is when your initial amount decreases significantly as time passes. Now, if it's a growth function, our base is going to be a positive number greater than 1. If it's a decay function, our base is a fraction between 0 and 1. Now, note that it can't be a negative number. So when we think decay, we think negative, but that's not the case here. So your base is actually going to be a fraction that's between 0 and 1. All right, how you can create your exponential growth or decay function is by using this formula down here. Now notice I have a plus or minus in the middle here. The plus or minus depends on whether it's a growth function or whether it's a decay function. So if it's a growth function, obviously you want to use the plus sign. And if it's a decay function, obviously you want to use your minus sign. Okay. Now I, because we notice it has an I here, I stands for the initial amount, whether that's what you're starting with. Sometimes we call it our principal if you're looking at the financial side of things. R is referring to your rate as a fraction. So that's how fast something is increasing or decreasing. And T is our time. And our time is usually in years in problems like this, but it could be in days or weeks or months or whatever it may be. All right, let's take a look at a example real quick here. It says a sofa depreciates at 20% of its original value each year. If the sofa was $349 at its time of purchase, what is the value of the sofa after 4 years? Round your answer to the nearest cent. All right, so there's some information here. It's depreciating, right? So that means we have an exponential decay. The rate is 20%, which is 0.2 as a decimal. The initial amount, so the starting amount, was $349. And the time we're looking at is after 4 years. Good. So we're going to use the formula I, which is our 349, and our rate is going to be 1 minus 0.2, right? Because we're looking at decay. So we want 1 minus 0.2 to the 4th power. And for those that are wondering where this formula is coming from, it was on the previous slide. So remember that's 1. We have that plus or minus r to the t power there. Order of operations is really important as we're solving these. So make sure you're doing your exponents first before you're multiplying. Otherwise, you're not going to get the correct answer. So again, make sure you're doing your order of operations. Okay. And then if we multiply that by 349, we get approximately $142.95. All right, I have one problem that I'd like you to attempt before our live class, and it is as follows. You need to solve the exponential equation below here, where it is 6 to the negative 2a power equals 6 to the 2 minus 3a power. I will be asking for your answers as soon as we start class. And then once you give me your answer, I can let you know if you are correct or incorrect, and then you can begin working on the problems in the breakout rooms. All right, thanks for watching this all the way to the end, and I will see you in the next live class. Bye, everyone.